Okay, for this video, I'll be going through kinematic success criteria D. Interpret given examples of non-uniform acceleration. Now, take note, acceleration is defined as the rate of change of velocity. Okay, the rate of change of velocity. That means how much the velocity change every second. You can take it as that. Okay, or how much the velocity change per unit time. Okay, so let's look at the first example. Okay, non-uniform acceleration occurs when the change, either increase or decrease in velocity per unit time, is not the same. Okay, so this is the time axis. So every time the car appears, it is 1 second, right? So 0 to 1, 1 to 2, 2 to 3. Okay, so we set the unit time to be 1 second. So initially, the initial speed of velocity of the car is 0 meter per second. Now, sometimes you'll hear me talking about speed and velocity interchangeably. Okay, because the car is moving in a straight line in one direction, therefore the speed is equivalent to the velocity, right? Because velocity is actually speed in a certain direction. Okay, so at time equals to 0, the speed or the velocity of car is 0 meter per second. Now, after 1 second, the velocity becomes 30 meter per second. So if I were to use this time frame of 1 second to calculate the acceleration, A equals to V minus U over T, I will get 30 minus 0 over 1, so it will be 30 meter per second square. So this value of 30 meter per second square tells me if the car is going to continue with this acceleration, every second the speed or velocity will increase by 30. Okay, but let's continue. After 1 more second, from the first second to the second second, okay, we check that the car's velocity is actually now only 50 meter per second. That means there is only an increase of velocity of 20 meter per second. So if I were to calculate the acceleration in the second second, from the first to the second second, I'll use the formula A equals to V minus U over T again. The initial, the final velocity is 50, but now I got to use the initial velocity of 30 because now I'm examining this time frame. So 50 minus 30 over 1 second, it will be 20 meter per second square. So if you were to compare acceleration of 30 meter per second square and 20 meter per second square, of course, this acceleration is higher, right? The higher the value, the higher the rate of change of velocity. Okay, now maybe I use blue for the last part. From the second second to the third second, also taking 1 second, we see that the velocity is now reaching 60 meter per second. Okay, compared to at the second second, the velocity is 50 meter per second. Let's do our final calculation. A equals to V minus U over T. So the final velocity is 60 minus initial of 50. Now the time is 1. So we have an acceleration of 10 meter per second square, right? So you see that the acceleration actually decreases from 30 meter per second square, okay, to 20 meter per second square to 10 meter per second square. That means overall the acceleration is not constant. Not constant. Okay, let's compare with what if the acceleration is constant at 30 meter per second square. Okay, so let's say in the first second it is having an acceleration of 30 meter per second square, but we want it to be constant. Okay, so after 1 second, the velocity will be 30 meter per second. After 1 more second, if the acceleration is constant still 30 meter per second square, then now the velocity will be 60 meter per second, because the change in velocity is 30 meter per second. And if I were to give it one more second, and if I want it to be constant at 30 meter per second square, so the acceleration is still 30 meter per second square. But acceleration is the rate of change in velocity. So now the velocity went from 30 to 60 and then to 90 meter per second. So having a constant change of 30 meter per second every second. Okay, you might want to replay this part to familiarize yourself with this concept. Okay. Okay, something else that I would like to point out here. So the acceleration actually is not constant. It went from 30 to 20 to 10. Okay, the acceleration is not constant. And I also see that the acceleration is decreasing. The acceleration is decreasing, right? It went from 30 meter per second square to 20 meter per second square to 10 meter per second square. That means the amount of velocity changing is not the same. In fact, it is decreasing. But does it mean that the object is slowing down? Okay, does it mean that the object is slowing down? Because the acceleration is decreasing. So my question is the object slowing down? Is the object slowing down if acceleration decreases? Okay, think about it. Okay, now I'll explain. You see, even though the acceleration decreases, right? It went from 0 to 30. That was the initial acceleration of 30 meter per second square. Then it went to 30 to 50, so the acceleration becomes 20 meter per second square, and finally to 10 meter per second square. But you see that overall, the velocity is still increasing. It's still increasing. It went from 0 to 30 to 50 to 60. It did not slow down. Okay, so no, the object is not slowing down if acceleration decreases, because the word of acceleration means that velocity increases. Okay, it means that velocity increases. But what do we make of this word decreases? Right? Acceleration, look at the red color box, it means that velocity increases. Okay, but now we have a case whereby the acceleration is decreasing. Okay, so later you will learn that the velocity increases at a decreasing rate. Okay, so this is something that I will be going through later on. Okay, so you just maybe watch this video again and think about this concept. Okay, so besides non-uniform acceleration, there will also be non-uniform deceleration. Okay, so you can look at this. Initially, it was 60 meter per second. After 1 second, the velocity decreases to 40 meter per second. Okay, so maybe you do the calculation. A equals to V minus U over T. A equals to final velocity is 40 minus initial is 60. Over time 1 second, we get negative 20 meter per second square. So what does the 20 means? It means the value that the velocity changes, right? It went from a value of 60 to 40. But how about the negative? It tells me that the car is going from left to right. Okay, left to right. You see that the car is going from left to right, and left to right is positive, but the acceleration is negative. That means a deceleration was applied to slow down the car. Okay, So take note of the negative and positive. It may be very confusing at first, but after a while when you do more questions, you'll start to get the hang of it. Okay, let's continue the car's journey. From the first second to the second second, okay, the velocity again decreases from 40 to 30, and that to me it is deceleration. So again, I can calculate A equals to 30 minus 40 V minus U. This is my V, this is my U, yeah? Over time, so equals to negative 10 meter per second square. Okay, so you see that the slowing down of the car is not as much as the first second, whereby it slowed down by 20 meter per second. From the first to the second second, it slowed down by 10 meter per second, not as extreme. Okay, so let's examine the final part. From the second to the third second, right? It went from 30, so now this is no longer V, this is my U, this is my V. Okay, because now I'm taking this to examine. So we have the initial of 30, the final of 0. So A equals to V minus U over T. The V is 0 minus 30 over 1 equals to negative 30 meter per second square. So you see, for this last part, right, it went from 30 to 0. It has actually the greatest deceleration, the greatest drop in speed, from 30 all the way to 0. Okay, look back, it dropped from 60 to 40, a drop of 20. Okay, then it dropped from 40 to 30, a drop of 10. And in the last second, it actually dropped from 30 to 0. So that is the largest drop. Therefore, it will have the largest decrease in velocity, and therefore the largest deceleration. Okay, and because the value is not the same, 20, 10 and 30, so it is not a uniform deceleration. A uniform deceleration will look something like this. Okay, let me constant deceleration will look something like this. We started off with 60 meter per second, okay, and after 1 second it dropped to 40 meter per second after 1 second. Okay, and if I want a constant deceleration, then after 1 more second it will drop by 20 meter per second, and finally after 1 more second it will drop to 0 meter per second. Okay, so we see that it keeps dropping by 20 meter per second, 20 meter per second, and 20 meter per second. So this is constant. This example is constant deceleration of 20 meter per second square. There is no positive, there's no negative to it, because deceleration already tells me that the velocity decreases.